Welcome to Kang Academy. My name is Salman Kang, and with me is
Kevin Yu.
Say hi, Kevin.
Hi guys, how are you doing?
I'm doing good, Kevin. How are you?
Great. No.
So now, we'll be teaching you about free body diagrams. A free body diagram, also called a force diagram, is a pictorial representation of unique forces acting on a body of interest. The purpose of the free body diagram is to be able to understand how the forces interact with each other and delineate insights about the motion and the forces acting on the object in specific directions.
So to begin, we start with a simple example. So if a block is at rest on a horizontal surface, such as a table, we can draw a free body diagram to pictorialize the forces acting on the block. Since the block is not accelerating, the net forces in both the y and the x direction are zero. The force of gravity points downwards, while a normal force exerted on the block by the table exerts an equivalent force upwards because of Newton's first law. There are no forces horizontally, so it's zero. Basically, as from the equations on the right, you can see that at the end of the day, the sum of forces equals force of normal minus force of gravity, and then sum of the forces is zero, so the force of normal equals the force of gravity. As a side note, Mr. Klingler will really want you to draw free body diagrams on tests. Even if you don't know how to do the problem, just draw a free body diagram of the situation, because it's usually worth a lot, maybe a couple points here and there, and that amounts to maybe 10–15% of your test. So do draw free body diagrams.
Okay, so another tip is that you don't have to actually draw the entire object when you're drawing the free diagram. You can just draw a simple dot, or in this case we drew a simple little box, and then draw the forces coming from the object. Now, Mr. Klingler is pushing a case of Diet Pepsi along a frictionless floor. Say hi to Mr. Klingler.
Yay!
Hi! Let's say that right now he only exerts a horizontal force to the right, so no vertical force involved. So, as a result, the block accelerates to the right. In this free body diagram, we have the same vertical forces involved as the earlier example. But this time, we have a horizontal force involved. Therefore, we will draw an arrow to the right in our simplified free body diagram. This will be especially useful in visualizing the situation when you are asked questions such as about the speed or the nature of the motion of the case of Pepsi.
Okay, so now what if Mr. Klingler is dragging the case of Pepsi using a rope across the same frictionless surface? This rope is angled upwards, and the tension in the rope exerts a force both horizontal and vertically. With force diagrams, you will also want to make sure that the relative sizes of the forces are clear. This is done by drawing certain forces longer or shorter. For example, we know that the force of Mr. Klingler pulling up on the case of Pepsi will lessen the normal force exerted on it. Thus, it will be smaller than the force of gravity. Draw the normal force pointing upwards, but shorter than the force of gravity. Make sure to include the force of gravity that still acts downwards and the force of tension on the rope acting on the case that is pointing at an angle towards the right. Also, in this case, if we are to introduce friction, this will be moving against the motion, and let's say if Mr. Klingler is pulling towards the right, the Pepsi can is moving to the right, so there will be a force of friction, also shown on the free body diagram, pointed towards the left.
So, let's say Mr. Klingler wants to push the case of Pepsi, push down on it from behind. Well, definitely we can imagine that he would exert a force downwards, as well as horizontally. This would increase the normal force exerted on the case, since the floor, or table, or whatever, will have to exert a greater force back upwards to counteract the combined downwards force of Mr. Klingler's biceps and the force of gravity. Now, in this case, if we want to talk about friction again, we will have, since in the case before, the normal force is greater in this case because the force of gravity, combined force of gravity and the combined force of Mr. Klingler's biceps is greater. As a result, since the force of friction depends on the normal force and the normal force is greater, the frictional force opposing the direction of motion will be greater in this case.
So finally, we are presenting you with a slightly more involved example of using free body diagrams. If you want to do this yourself, just pause the video here. So in this problem, we have a case of Pepsi on an incline. As you can see, there's a rope attached onto the corner of the case, and on the block, the force of gravity still acts downwards on the Pepsi, but normal force is always perpendicular to the surface of interest, so the force comes out at an angle. However, as you can see, the force of tension in this rope reduces the normal force acting on the block, and so keep in mind somehow this normal force is not as simple as usual. And if you want to add friction, you can, which will make this problem a little bit harder, especially depending on which side you want the block to go to begin with. So this wraps up our presentation on free body diagrams. If you have any questions or concerns, please.
It's hard to look right at your